Welcome back to Chapter 14 of Earth Science, Ocean Water and Ocean Life. Now, this is a bit outside my realm in terms of geology, but I've had several oceanography classes, and well, I love the ocean. As I said in the previous chapter's lecture slide, it's just been a part of what I've loved to learn about since I was a kid. So let's dive in, right? All right. Seawater consists of about 3.5% by weight of dissolved minerals, and much of that is salt. So it's the total amount of dissolved material in the water. There's a lot of stuff in seawater. You don't realize it. And it's typically expressed in parts per thousand, with an average salinity of about 35 parts per thousand, which is mostly sodium chloride, which is the chemical name for salt, table salt, the same stuff you shake on your French fries. Now, some areas are saltier than others, like let's say the Dead Sea, which is really not a sea, it's an inland lake, has so much salt in it that you can just float. You don't even have to do anything. You'll just float in the water. You do float typically a little better in the ocean than you do in, let's say, a freshwater lake, but nothing like the Dead Sea. The Dead Sea is so salty that it just holds you up. So the dissolved components in seawater are, it's mostly water, 35 grams of salt, most of which is sodium chloride, but there's some other things in there too. So, sulfates and magnesium and calcium and potassium. The idea being that is, that 35 parts per thousand is still quite a bit of salt. And obviously, if you've ever been in the ocean, it definitely tastes salty if you get it in your mouth. You don't want to drink that stuff though, because it'll kill you if you drink too much salt water. But there's other things besides salt in the seawater. Now, the sources of the salt come from chemical weathering of rocks and what's called outgassing from volcanic eruptions, both from underneath the ocean and, obviously in the air. The variations are a consequence of, the changes in the water content. The density of the water can change, and we'll talk about that in terms of temperature and, whether it's at higher latitudes or lower latitudes. But not all ocean water is the same exact salinity. There are some areas that have a bit more salinity than others. Now, there are different processes that decrease the salinity, things like precipitation. If you add fresh water, you're going to take away from the salt water. That makes sense, right? Runoff from land. Again, the water coming off the land is not salty. It's fresh water. So you're sort of diluting the ocean in that little region right there. I mean, you're not going to dilute the entire ocean. Icebergs and sea ice melting. Obviously, that adds a ton of fresh water to the mix. Now, there are things that increase um, salinity, which because they're removing water, things like evaporation and the formation of sea ice. So when sea ice forms, it sucks out all of the fresh water because that's what's freezing, leaving behind a much saltier sort of brine behind. So the salinity in the open ocean can vary between 33 parts per thousand to 38 parts per thousand. So it just depends on where you are. It's not a huge difference, but it's definitely noticeable, at least in the chemistry. Maybe not, to us humans, but so um, here's an image showing the variation of salinity throughout the oceans, and you can see how it changes quite a bit depending on where you are. At the higher latitudes, up here in the colder areas, you have a tendency to have lower salinity. In the warmer equatorial regions, you have higher salinities here in some of these areas. And you'll notice this right here, and there's this much lower salinity here because that's where the Amazon River empties into the Atlantic Ocean. The Amazon River is the largest river, one of the largest rivers in the world. So there's a lot of fresh water being pumped out of there. Now there's different reasons for some of this. You can see there's lower salinity here, and that's in a much warmer area. That could have to do with ocean currents as well. It's not strictly just based on climate, because obviously, this is a higher salinity up here, and that's at roughly the same latitudes we're at. So it's not strictly latitude based. A lot of it does have to do with world ocean circulatory patterns. Now, in the low latitudes, you have higher temperature at the surface and a rapid decrease in temperature with depth, what we call a thermocline. Now, if you've ever scuba dived before, and I knew how to do it at one time, when you first get in the water, you feel that it's usually, in the summer, let's say you're in the summer, and about all of a sudden you're going down about 10 feet down, 50, all of a sudden the water temperature changes drastically. It gets much cooler. Not cold necessarily, but cooler. If you got a wetsuit on, you really notice it because that's what the wetsuit's for, to keep you a little warm in the colder water. Now at the high latitudes, you don't have that phenomenon because the surface water is already cold, so it's cold all the way down. So, that's just something you have to deal with. If you have cold surface temperature, you don't get that phenomenon. You can see that in this graph. So at the low latitudes, with higher temperatures, you have this thermocline, this region where you have this gradual change where it starts to get cool, 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 and then it really just kind of levels off. Whereas at the high latitudes or the polar regions, it's just straight down. The water, because it's already got cold at the surface, just keeps being cold. Now there are unique thermal properties um, that make it resistant to temperature changes. Excuse me. Water is one of the most interesting liquids, obviously, or substances on Earth. Like, for example, just an odd thing, most materials, when they freeze, they contract, right? They shrink. Um, but water is just the opposite. When it freezes, it expands. That's why if you leave something in the freezer, let's say a bottle or a can of something, and it blows up, because the water in there expanded and burst open through its container. So the same thing sort of applies with some of these thermal properties. Water is really weird that way. You can get inversions where you'll have colder water, then warmer water, then colder water. It kind of gets trapped in there, depending on circulatory patterns and things like that. And then, because of global warming now, you see slight changes in ocean patterns where there never used to be. Now, you might have heard of El Nino and El Nina. Um, and that's where you have cold water where there should be warm water, or warm water where there should be cold water. And that's in the Pacific Ocean, usually off the coast of California and Mexico. And that can drastically change our weather patterns here. Typically, if there's an El Nino, which is a colder than normal ocean temperature, we get warmer winters. It pushes the cold air back up into Canada, and on average, we get more warmer days in winter during El Nino. And then El Nino, which is where you have all this warmer water coming in, we have a tendency to have colder weather because the jet stream is lower in the United States, allowing all that cold water from Canada to come down. So the ocean plays a huge role in the weather, even thousands of miles away from the ocean where it's taking place. Here you can see sort of the temperature and salinity variations depending on where you are in latitude. So right here is the equator. Okay, so they have the highest temperatures, but some of the lowest salinity. The reason why you get higher salinity here, for example, or here, is that's where you start to get ice to form. So when the ice forms, you get things like, then it takes the fresh water out of the mix, leaving behind a saltier brine. Now, ocean density is something that we talk about not so much because in freshwater, because there's no salt, right? Ocean density or salt in the ocean gives the ocean a higher density than freshwater. That's why, like I mentioned in a previous slide, you can float at the Dead Sea. In the Dead Sea, there's so much salt, the water's so dense, it'll actually hold up a human body. So that determines the amount of how heavy something is, determines where it sits in the ocean. And a lot of that has to do with salinity and temperature. Now, at the low latitudes or equatorial regions, you have low density at the surface and it increases rapidly with depth because of the colder water. So, colder water is denser, it's more tightly packed. And then at the high latitudes, it's it's cold at the surface already, so there's very little change. So similar to the thermocline in the high latitude, or excuse me, low latitudes, where you have warm water at the surface and it just like gradually gets cold and then it gets cold. You have that sort of tapering off. The same thing applies with density. Warmer water is less dense. So if you have warmer water at the surface, there's a gradation between where the warm water is till it starts to get cold. Not only does the temperature decrease, but the density increases. So here is an example of that. Now, if you remember the thermocline, the thermocline started here and went this way, and that was temperature. So it's the sort of the inverse of temperature. But this is in the low latitudes, the density. So you have warm water, which is less dense, and then it goes through the sort of this gradation to the point where then it has a higher density. And again, at the high latitudes, the water's cold all the way through the water column, so the density changes very little. So in the ocean, there's three main structures when it comes to ocean depth. You have the surface mix zone, which is where we swim. For example, the very upper part where you have the sun, you have mixing, you have the waves, the upper, in this case, 300 meters, which is 900 feet, but we're only swimming in the first like 20 feet, right? Unless you're scuba diving. But the upper 900 feet, 300 meters or so, that's where the sun plays a role in warming the surface of the earth, or excuse me, surface of the ocean. Below that, we have what's called the transition zone. That's the layer between what's being warmed by the sun and then where you get into the very deep zone. This is where the thermocline and the pycnocline are. So the thermocline is dropping off towards the colder temperatures and the density is ramping up towards where the colder temperatures are. So it's that inverse effect again. And then finally, you have the deep zone, which is where like the vast majority of the ocean sits, where no sunlight ever reaches this zone. It's always dark. The temperatures are just a few degrees above freezing, and it's constant high density water. Now, we haven't talked about pressure yet, but that's where you get into the higher pressures as well. So, you know, the water doesn't freeze because of the high temperatures, or excuse me, high pressures. That's why I bring up pressure now. So it says it's just a few degrees above freezing. Yes, it's very, very cold, but it doesn't freeze because of the pressure. Pressures involved that deep. So here's a kind of a schematic of that. You have the surface mix zone, which is the very upper layer. Like I said, in the grand scheme of the oceans, 900 feet is nothing when it goes down to 29,000 feet. So it's the very upper zone. And then you have the transition zone, which is, where light can still reach. But this is where temperature is decreasing, um, and density is increasing. And then you have the deep zone, which is the vast majority of the ocean, where there's no sunlight whatsoever. That's why, it's the last, we've been to the moon, but there's many places in the ocean no man has been yet because it's vast and dark. Now, there's obviously massive amounts of marine and life in the ocean, a wide variety, but most of them live within the surface, near the surface where photosynthesis takes place. They need sunlight. Most organisms need sunlight. Not all, but most. So things like plankton, which are the floaters, I don't know, I always think of plankton from SpongeBob right away, but you get the idea. Different types of algae, animals, that we talk about, uh, fish, whales, sharks. And then there's bacteria that live in this area, in this region, sort of these upper regions where the sunlight can still penetrate. And the bulk majority of Earth's biomass that lives in the ocean, the vast majority, 90 some percent of it, lives within this upper zone where sunlight can still reach. The upper, we'll say 900 feet or so. So here's a look at some of the phytoplankton, things like diatoms, which are these sort of elongated things here. Um, these are just the tiny itty bitty base of the food chain, so to speak, that live in the upper parts of the ocean. And then you get into the zooplankton, things like squid larvae and copepods, and copepods are kind of like these little mini shrimp looking things here, and snail larvae, fish larvae, worms, um, for radiolarians. Now, there are animals that eat this stuff, and then animals that eat those and eat those. You get the idea. So this is the base of the food chain, and what is dominates the type of life found in the ocean. This is these tiny little things, many of which you can't even see with your naked eye, is what dominates the type of life found in the ocean. So you have what are called the nekton, which are the swimmers, all animals capable of moving independently of the ocean currents. So they're not floaters. I think like jellyfish are considered floaters. Uh, they're unable to move throughout the breadth of the ocean. So here's your nekton. You've all seen these before, right? You got your sharks, your cuttlefish, whales, and fish. So just there's a zillion of these types of creatures in the sea. I love cuttlefish; they're cool as heck. Then you have the bottom dwellers. Now that doesn't necessarily mean they live in the deepest parts of the ocean, but they live on the bottom, what we call the benthos. Um, they exist in shallow coastal floor, but most live in perpetual darkness in deep water. Things like this. And some of them are very, very odd looking, right? You've probably seen some of those specials where you have these really weird looking animals floating, skittering about on the ocean floor. Starfish, types of starfish, and tubes, worms, and the just all kinds of really cool stuff. Now, what you see on here, you just so you understand, is these are taking with very powerful lights. All of these animals live in complete and utter darkness 24/7. They usually adapt to that in various ways, whether it be they make themselves bright with phosphorescence, or you know uh, they're filter feeders where they just kind of put these things out in the water and they grab whatever floats by, things like that. Now, there's several factors that are used to divide the ocean into marine zones. So just like the ocean has, sort of the upper mixing air, the surface area, the mixed area, and the deep area, the same thing applies to where the most of the life is found, and it's mostly based upon the availability of light, the photic and the aphotic regions, and that's because a lot of the ocean life that it requires sunlight. Most animals do, not all, but most do. It's the upper part of the ocean. It's sunlit, and then yeah, you have the euphotic zone, which is where the light is really strong. Think of that as like a shallow coral reef, right? I was in Key West last year, and the reef is about 15 feet down, if that, or 10 feet down. It's right there at your feet, pretty much. So they get sunlight all day, every day. And then you have the deep ocean with absolutely no sunlight. And it's a very foreign thought when you think about it. If you live in Alaska in the winter, the sun barely gets over the horizon, but there's still a little bit of light. This is absolute pitch black. You will never ever see your hand in front of your face, the darkest black you've ever seen, all the time. If you've ever been in a cave, and I used to go caving quite a bit, it's the blackest thing you can imagine. You can't ever you could put your hand right in front of your face and just wait and wait and wait, and your eyes will never adjust. You'll never see your hand. It's that dark. It's just the blackest pitch black you've ever seen. And that's what it's like in the deep ocean. Now, another factor that plays a role is the distance from shore. So you have what's called the intertidal zone, which is what's affected by the tides, where the waves crash on the beach, and you know, where the land and the ocean overlap, so to speak. Um, and that's depending on how big the tides are, that could be anywhere from a half a mile to a mile offshore, depending on where they are. Then you have what's called the neritic zone. The neritic zone is just past the lowest point of low tide, and everything out to the shelf break, the continental shelf break, which we talked about in the last chapter. This is this sort of shallow ocean. I use shallow, not in terms of humans, it's still pretty deep, but in terms of the ocean, it might be 2,000 feet deep, but then drop down to 10,000, 12, 13,000 feet where you reach the oceanic um, zone past the continental shelf where it really drops down into the depths. So these are the three main zones, and much of the creatures that you and I know live in the middle zone, actually, not the intertidal zone. That's more, that could, because like corals couldn't live if the tide goes out. If the tide went out, they'd get, you know, in many of those areas, they wouldn't survive. So most of the sea creatures that we know live in the Neretic zone, which is, just outside of the reach of the tides. Water depth, you have what's called the pelagic zone. The benthic zone, which is, the real deep, it's sort of the middle zone, and then you have the abyssal zone, um, a subdivision of the benthic zone, which is just, it's the deepest of the deep. Extremely high water pressures, extremely low temperatures. It might, if ice freezes at 32 degrees Fahrenheit or 0 degrees Celsius, the water might be 1 degree Celsius or 33 degrees, 32, 33 degrees, but it doesn't freeze because of the pressures. There's no sunlight and very sparse life. It's their only food source is decaying particles that float down from below, or excuse me, from above, or large fragments. And I've seen this in ocean specials where a whale will die and it'll float down to the bottom in the depths, and it'll be food for years down there. It'll take years for the tiny little critters that are down there to eat up that entire whale. It'll be there for a couple of years. They did a study on that where they kept coming back. I think it took like 2 years for that whole whale to get finally down to bones. Very, very interesting. So here's a schematic of that, so to speak. You have that intertidal zone, which is where we swim. You have the Neretic zone, which is just past all of that. Right here is, and then you start getting into the ocean zone. You have the benthic, and then you get way down here to the abyssal plain, and that's, you just don't see very much life down there anymore. And you'll notice that the sunlight here can only go down, you know, the sun doesn't penetrate very much of the water. You think it does, you think of, warm ocean coral reefs, but it doesn't take long before the sunlight doesn't penetrate the ocean. So what determines ocean productivity? Meaning, why are there more marine creatures in some areas than others? And part of that is, is it is there sunlight available? Is there chemical reactions taking place that allow the organisms, the availability of nutrients, and I'll get to that in a second, the amount of solar radiation, obviously. Um, but most abundant life forms exist where there's a lot of food, right? That makes sense, nutrients, and good sunlight. So one of the places there's places in the ocean where you what we call upwelling, and what that is where you have all this cold water that comes up from the ocean depths, bringing with it all of these nutrients. And you'll see this, there's places in the Caribbean that have this, and that's where they have what are called wall dives, or like wall shelves of coral, where it's just, there's one, I forgot where it is. I think it's the Netherlands Antilles, like Bonaire. Where I've always wanted to go scuba diving there. It's one of the best wall dives in the world. The wall drops down something like 1,000 feet straight down, so it's like black when you look down. But you have all of this life on this wall because the water comes up from the depths, bringing with it all of this nutrients, and it's already in the sunlight. So it's the best of both worlds, and you just get this area just teeming with life. Now, in the polar oceans, you get nutrients rising from deeper water. Um, and so high latitude surface waters have high nutrient concentrations. Now, if you've ever noticed where a lot of fishing places are, like the Japanese love their fish and they fish a lot of the ocean. A lot of them are in northern latitudes. A lot of the big fishing vessels are found in northern latitudes because the colder water has more nutrients in it. However, on the flip side of that, the low solar energy, because the sun's higher or has a lower angle, it doesn't allow for things like coral reefs, right? You're not going to find cold water coral reefs because there's not enough photosynthetic energy to keep those things alive. So yes, the water has more nutrients for the fish to feed off of, but you're not going to get those, the Great Barrier Reefs type thing in the higher latitudes. Here's a graph showing the difference between when the diatoms sort of peak and then when the zooplanktons peak. Now, why is this important? The zooplankton feed off of the diatoms. So the diatoms have their highest point in early spring when the water's still cold and these nutrients are high, and then they start to tail off. Well, right after that, the zooplankton kind of kick in and then tail off because they're feeding on the diatoms. So you need to, again, it all goes back to the food chain. These tiny little critters that you can't even see with your naked eye are the ones that feed everything else. So you have the diatoms and the plankton down here at the bottom. They feed the zooplankton. The zooplankton feed this, and it goes right up the line. So, but it all starts at the base, and this is sort of the peak season for it is right here in spring when you have that cold water with all the nutrients in it. That's with the diatoms. They feed off of that, and then it goes from there. The zooplankton and everything else. Now, productivity in tropical oceans are low in the open ocean because the thermocline, that high, there's high temperatures at the surface, then they gradually go down to cold. It eliminates much of the nutrients from the deeper waters below. It can't, it doesn't well up from the bottom like it does in the high latitudes. So typically, equatorial regions with high surface temperature, they have less nutrients than the colder temperature waters near the polar region. In this graph, you can compare productivity based upon their latitudes on Earth here. So here's looking at phytoplankton, and you can see the tropical line here at the bottom, the red line, is steady pretty much, even though it's lower, it's steady all year long because in the equatorial regions, they get the same amount of light, which, but because the water's warm all year long, it has a low productivity. And then here in the mid latitudes, kind of where we are, you get that sort of peak in the spring because the water's still cold, it's coming up, everything's starting to ramp up, and then it gets low during the warmer because the surface waters get warmer again, peaks a little bit in the fall and then goes back down. In the polar regions, you can see it's very low and it just spikes straight up right around June, July because that's the warmest part of the year for that particular region. That's as warm as it's ever going to get is that narrow window. But it's a high peak though. Now, productivity in temperate oceans, which is kind of where we are, we're at 43 degrees north. So in the winter, they have low productivity because the days are short and the sun angle is low. That makes sense, right? So you're not going to get a lot of productivity when you don't have enough sunlight. The water might be cold, but you got to have both. You have to have the cold water and the sun in both. So in the spring, you have this huge bloom of phytoplankton that's quickly depleted because even though you have more sunlight, the productivity is limited because the water warms up fairly quickly. So you have a narrow window where you have this big spring bloom. Now, summer, you have a strong thermocline. The surface of the water gets really warm. So the nutrients aren't replaced from below, and so the phytoplankton stay relatively low. And you saw that in the graph in the equatorial regions, it stayed consistently flat almost all year long because it always has that thermocline, and it can't the nutrients can't come up from the below. Now in fall, the thermocline breaks down. You get the nutrients return to the surface, and you get another short-lived fall bloom for phytoplankton, which we saw that little tiny spike in September and October. So the highest overall productivity occurs in the temperate regions because you get these spring blooms that just go nuts where you open up that window, but when you open that window, it's opening a ton of productivity. So here's another graph showing the temperate oceans in the northern hemisphere over the course of a year. And you can see the amount of sunshine. Let's start with sunshine. So the sunshine gets obviously greater over the summer months and then gradually comes back down over the fall and winter months. So how does that compare with some of the um, types of marine organisms? Well, you have the phytoplankton, which we just saw. They have a huge peak here in spring, and then it quickly drops off, and then another peak in fall. So that's where you have sort of that balance between cold water and enough sunlight. You get sort of the best of both worlds. Whereas for phytoplankton in the summer months, you have warmer water because you get that thermocline again. And here uh, you have the red line here, which are the nutrients. The nutrients are highest in the colder months. They drop down and then they come back up. They drop down in the warmer months. The zooplankton have their peak again, kind of right after the phytoplankton, which makes sense because that's what they're feeding off of. They have a small bump again in late fall here, but it follows a general path, just not as much of a spike as the phytoplankton do. Hopefully you can start to see the trends that are occurring. The colder water holds the nutrients, the warmer water does not. Partly because of the thermocline, partly because it can't. There's not enough nutrients. The water is too warm. So that's what I want you to get out of all this is the colder water brings up the nutrients, feeds the phytoplankton, feeds the zooplankton. Once you get into the warmer months, the water gets too warm, develops the thermocline, which doesn't allow the cold water to come up. That's all of it in a nutshell. So you have all of these feeding relationships, part of the food chain, food web thing, starting from algae and working your way up. And only a small percentage of the energy taken into any level is passed on to the next. Now, let me explain that as we go along here. They have these things called trophic levels. So it's the chemical energy stored in the mass of the ocean's algae that's transferred to the animal community most through feeding. So how much energy, if this thing is eating this thing, how much energy does it get? And then does the next step in the line carry over some of that energy? And what you'll see is that it's a very inefficient system where only about 2% of the energy is being transferred from what's being eaten to what ate it, essentially in a nutshell. So here's a graphic just kind of showing you what that is. So for every 500,000 units of radiant energy, you get 10,000 units converted at trophic level 1 biomass. All right. So the sun's not even is not great at converting the energy needed for the phytoplankton. Then you get 2% efficiency. That's not very good, is it? So then from there, you have the zooplankton eating the phytoplankton, and that's about a 10% efficiency, which is better. And then the fish eat the zooplankton, that's about a 10%. So you'll see the first one is only 2% efficiency, so 98% loss. That's why there has to be so much phytoplankton available because it's the base of the food chain. This is a food chain in a nutshell. So the more phytoplankton you have, the more zooplankton you have. The more zooplankton you have, the more fish can eat. The more fish can eat, the more the bigger fish. You get the idea. So it's all interrelated. And it all starts with the sun. So the food chain is a sequence of organisms in which the energy is transferred. And then the food web is sort of the more complicated version of that, involves feeding of different animals. And rather than just looking at it as a linear process, it's sort of this web. And let me show you an example of that. So here's a food chain and a food web for the Newfoundland herring fish. Okay, so in a typical food chain you'd see here, it's very linear. It goes straight up. You have diatoms to copepods. Copepods eat the diatoms. You got to work backwards. Even though the arrows are pointing up, the herring eat the copepods. The copepods eat the diatoms. That's sort of the basics, the version of what we would consider a food chain. However, we all know it's got to be more complicated than that. And I'm not going to go into all of this, but there's a lot of things. If you start at the bottom with the diatoms, these are the phytoplankton back down here, right? From there, you have all of these other things eating him. So the mollusk eat the diatoms, and then the wood arrowworms eat the mollusks, and then the herring eat the worms. And you get the idea. So the what it is herring eat more than one type of food. So it's not just copepods they're eating. They eat all of these things. So you have to account for all of that, but it all starts at the bottom with those phytoplankton, the diatoms and the dinoflagellates. Um, and so all of those, without those at the bottom, the whole thing starts to fall apart. Okay, so that was it in a nutshell. I know this was a pretty quick one. What you need to get out of this is that the ocean is divided up mainly into three zones, right? You have the mixing zone, the transition zone, and the deep zone. The bulk of the animals we know and love all live within the reaches where sunlight can reach. That mixing zone, the upper roughly 300 meters, about 1,000 feet of the ocean. Anything after that starts to get real dark. You transition, and then you do get those benthic organisms, those weird looking things that scurry around in the dark, perpetual darkness. But it all starts with the food chain and the food web. Without the phytoplankton, you don't have the zooplankton. Without the zooplankton, you don't have the fish. Without the fish, you don't have the bigger fish, and it goes right up the line. So, and where that occurs on Earth is highly dependent on the amount of sunlight that's given and the sort of the ocean circulation patterns where you have the colder water that can hold the nutrients better, and then the time of year where the surface water does or does not have the thermocline, which may or may not prevent it from the nutrients from coming up. With a thermocline in place, which is always the case in the equatorial regions, with that thermocline there, it's very difficult to get water to come up because it can't get through that thermocline. So that's why a lot of the fishing takes place in the cold waters. You see these shows like with the crab. I can't even remember the names of the shows off the top of my head where um, they're out of Alaska. Oh my God, I can't remember the name, but they're out of Alaska. So they're fishing in very cold waters because those cold waters have tons of nutrient and just tons of crab and fish laying around in there. Woo! I hope you got something out of this. And I hope hope you understand this a little bit. And I will see you on the next chapter. Take care. Bye.